This is an example of a spacecraft bus. It has solar arrays to generate electricity, reaction control thrusters for attitude control, orientation, and station keeping, a propulsion system for orbital maneuvers, a communications subsystem for telecommand and telemetry, and a star tracker for attitude determination. Note that this is just a generic example. JPL's spacecraft are different. For instance, they have no star trackers, since JPL's ground controllers command the spacecraft's orientation. In reality, most of JPL's missions do not involve Earth's orbit. However, there are always spacecraft in Earth orbit that help support JPL's missions, even though these spacecraft might not be directly related to them. These spacecraft are usually communications and navigation spacecraft, which are relatively common in Earth orbit. There are dozens of them and new ones are being launched all the time. This class of spacecraft is so plentiful because communications and navigation services are extremely important to our society. They are absolutely essential to modern warfare, economic activity, transportation, and many other aspects of daily life. Communications and navigation spacecraft are also very helpful to planetary missions. As we've seen before, whenever a spacecraft leaves Earth orbit, its mission operations are transferred to the Deep Space Network. A small part of the Deep Space Network is made up of communications satellites in geosynchronous orbit around Earth. These satellites enable the network to transfer data among the 3 ground stations in Spain, Australia, and California and JP. The Deep Space Network also uses several navigation satellites in the Global Positioning System constellation to keep accurate time. Time is one of the most critical parameters in the Deep Space Network. All of its clocks must be synchronized to within a few nanoseconds. The onboard clocks of the spacecraft are synced to the master clock at JPL. The master clock is, in turn, synced to the Global Positioning System constellation of navigation spacecraft, which are accurate to within a few billionths of a second. In the future, communications and navigation spacecraft may be deployed at Mars, Venus, or another planet to help missions in the vicinity. For instance, if there were to be a human mission to Mars, it would almost certainly deploy a communications satellite to help keep in touch with the crew. Right now, the Deep Space Network supports most of the missions in our solar system, including those at Mars, Jupiter, Saturn, Neptune, and Pluto. But in the future, there could be so many more missions that the Deep Space Network may need help. More communication satellites at strategic locations will be needed, such as Mars. Today, communications between Earth and Mars is carried out through relays between the Deep Space Network and orbiters in Mars orbit. Some of these orbiters are equipped for communications relay. They receive signals from Earth, store them in their onboard radioisotope thermoelectric generators, and retransmit them to the surface. Several Mars orbiters provide this service, but none of them are optimized for communications. Their primary scientific instruments take precedence over the communications equipment. And besides, communications is only one of their tasks. Orbiters like Odyssey, for instance, carry communications equipment to help support Mars exploration. Odyssey carries a communications transponder to forward commands and return telemetry to and from Mars. Exploration rovers Spirit and Opportunity and Mars landers Phoenix and Insight. The transponder is also used to forward commands and return telemetry from Mars orbiters. Mars Odyssey is powered by a radioisotope thermoelectric generator. That's why it can last so long in orbit. Its power output will remain strong until the mission ends. Communications equipment takes up space and adds weight to a spacecraft. That SY orbiter spacecraft do you want normally carry it unless there is a compelling reason to do so. If there is a large number of spacecraft on the surface, as there will be during a human mission to Mars, then communications equipment on an orbiter becomes much more valuable. Signals can be sent directly to the surface without having to go through Earth. This reduces latency and increases the overall communications bandwidth. The same is true for relaying signals back to Earth. Right now, the Deep Space Network communicates with Mars through relays between the network and the Mars orbiters. There are several Mars orbiters, and they come and go, so the network can always reach the surface. However, a Mars communications satellite would be much more reliable than orbiting spacecraft. Orbiting spacecraft have unpredictable orbits and sometimes pass behind the planet, eclipsing the sun and going silent for days or even weeks. Also, they move around, which makes pointing antennas at them challenging. A geostationary satellite over Mars would stay in a fixed position relative to the planet, making it easy to communicate with. Of course, the surface would have to know where to point its antennas, but at least the antennas wouldn't have to track a moving target. This is how a communications satellite over Mars could work. Signals from Earth would be sent to it and stored in its onboard batteries. Then the signals would be forwarded to the surface, and telemetry would be sent back to Earth through the satellite. The main challenge would be to keep the satellite in a safe region above the planet. If it were to fall into Mars' atmosphere, it would burn up just like any other spacecraft. But unlike most spacecraft, a communications satellite cannot survive a trip through the atmosphere and would have to be placed in geosynchronous orbit, far away from Mars' dense atmosphere. Placing a satellite in geosynchronous orbit around Mars requires a great deal of energy. Because Mars rotates slower than Earth, its geosynchronous orbit is much farther away, about 17,000 kilometers or 10,000 miles above the surface. From there, the satellite could see almost the entire disk of the planet. It would have to be slightly above the equator to avoid eclipses. The higher altitude would also mean that communications with Earth would be challenging. However, an orbit at 17,000 kilometers is still well above the thin upper atmosphere of Mars, so atmospheric drag shouldn't be a problem for a long time. Even if the satellite's orbit decayed and it entered the atmosphere, it would still have enough onboard fuel to raise its orbit and escape to heliocentric orbit before being destroyed. No Mars communications satellites have been funded or built as of early 2013. This concept is revisited in Chapter 18. The first example we'll discuss is NASA's Tracking and Data Relay Satellite System, TDRSS. The Tracking and Data Relay Satellite System is a constellation of low Earth orbit communication satellites used to support a variety of NASA missions. The system was launched starting in 1982 and grew to 6 operational satellites in 1995. The system was originally designed to support the Space Shuttle, but today it supports a wide variety of NASA missions, including the Hubble Telescope, Landsat, Topex, JASON, and UV. The International Space Station also relies heavily on TDRSS. The Tracking and Data Relay Satellite System is very similar to the former Apollo communication satellites. Both systems use low Earth orbit satellites to support spacecraft in low Earth orbit. However, the Apollo communication satellites were never meant to be a constellation. In fact, only 2 of them were ever launched. By comparison, the Tracking and Data Relay Satellite System was designed from the beginning as a constellation of 6 satellites. It had a backup satellite built in case one of the operational satellites failed. The Tracking and Data Relay Satellite System operates in 4 orbital planes that cross the equator at 38 degrees latitude. Each plane contains 2 satellites whose orbits are 180 degrees out of phase. This means that one of the 2 satellites in each plane is either in view of the ground station or of the spacecraft at all times. 2 operational satellites are always visible from the Goddard Space Flight Center in Maryland. This allows ground controllers to send commands to and receive telemetry from any of the satellites in the constellation. The Tracking and Data Relay Satellite System uses the Q and S bands of the radio spectrum. At any given time, each satellite is tasked with supporting one spacecraft. The assignment of a spacecraft to a particular satellite is based on the orbital characteristics of both the spacecraft and the satellite. Specifically, the relative inclination between the 2 orbits determines the amount of time the 2 vehicles spend in view of one another. This time is known as visibility. To maximize visibility, the inclination of the satellite orbit is matched to the inclination of the spacecraft orbit. The typical duration of contact between a relay satellite and a spacecraft is from 15 to 20 minutes. During that time, the spacecraft can download science data, upload new commands, and check the health of its systems. The Tracking and Data Relay Satellite System achieves a global coverage of 85%. This is what enables the International Space Station to rely on it. When a satellite passes overhead, it hands the station off to another satellite whose orbit takes it over the next ground station. The Tracking and Data Relay Satellite System is provided by NASA's Communications and Navigation Systems Program Office, which operates it in cooperation with the Goddard Space Flight Center. The Program Office is responsible for launching and operating the constellation of satellites, while the Goddard Space Flight Center provides tracking and relay services to customers on a 24/7 basis. Here is an illustration of how the Tracking and Data Relay Satellite System works. The white dots are ground stations.